Hey everyone, and welcome. With board exams just around the corner, I know ray optics can feel like a pretty big hurdle. But don't you worry. In this session, we're going to laser focus on the absolute must-know formulas to help you crush this section. Ready? Let's get right into it.
So tell me if this sounds familiar. You've spent hours memorizing every single formula. You feel like you get the concepts, but then you sit down with a numerical problem, and the answer just won't come out right. It's super frustrating, right? And trust me, you are not alone in feeling that way.
So what's the deal? Well, 9 times out of 10, the problem isn't the big, fancy formula itself. Nope. The real villain, the sneaky thing that's stealing your marks, is the sign convention. If you can master this one little thing, I promise you, almost every problem will just click into place.
Okay, let's kick things off with our first challenge, spherical mirrors. This topic is a guaranteed show up on your board exams, so let's make sure we've got the basics down cold by walking through a full example together.
And here it is, the one and only mirror formula. You've probably seen it a million times. Just a quick refresh. F is your focal length, V is the image distance, and U is the object distance. Now, let's put it to work. Imagine this problem. We place an object 30 centimeters in front of a concave mirror that has a focal length of 15 centimeters. Our goal is to find V. But before we even touch the numbers, we have to get our signs right.
Now, once we've figured out where the image is using that first formula, this next one tells us what it looks like. The magnification formula does more than just tell you if the image is bigger or smaller. That second part, negative V divided by U, that's the magic ticket. It tells us the very nature of the image. Is it upright or is it inverted?
And this is where the puzzle pieces come together. Let's solve our problem. For a concave mirror, the focal length f is negative, so f is minus 15 centimeters. The object is in front of the mirror, so u is also negative, minus 30 centimeters. Okay, plug those into the mirror formula, a little bit of math, and we get v equals minus 30 centimeters. Now for the magnification. M is negative v over u, so that's minus negative 30 divided by negative 30, which gives us minus 1. And that minus sign for m, it tells us instantly the image is real and inverted. The number 1, it tells us it's the exact same size. See? The signs tell the whole story.
Awesome job with mirrors. Now let's level up to our next challenge, lenses. The ideas are really similar, but there is one critical, tiny trap you absolutely have to watch out for.
Okay, look really closely here. Can you see it? It's just one tiny little sign. The lens formula has a minus, not a plus like the mirror formula. I'm telling you, this is one of the easiest mistakes to make when you're under pressure in an exam. You have to burn this into your brain. Lenses get the minus sign. Now let's try a new problem. An object is 25 centimeters in front of a convex lens with a 50 centimeter focal length.
So, let's find the image distance V for our lens problem. For a convex lens, f is positive, so it's plus 50 centimeters. The object distance u is minus 25 centimeters. We plug that into the lens formula, do a bit of algebra, and we find that v equals minus 50 centimeters. Now hold on, what does a negative v mean for a lens? It means the image is virtual. It's formed on the same side as the object. That's a huge difference from mirrors and a key point to remember.
And while we're on the topic of this lens, what's its power? Well, its focal length was 50 centimeters. And here's another rule you have to remember. For power, focal length must be in meters. So that's 0.5 meters. Power is just 1 divided by that. So 1 divided by 25 gives us a clean plus 2.0 diopters. That positive sign just confirms what we knew. It's a converging, convex lens. It all connects.
Okay, so we've been crunching a lot of numbers. But what does all this math actually look like in the real world? This is where ray diagrams are your best friend. They're like the visual proof that makes it all finally click.
Let's quickly trace one out. Imagine an object just outside the focal point of a convex lens. Rule 1. Draw a ray from the top of the object perfectly parallel to the main axis. When it hits the lens, it bends and passes right through the principal focus on the other side. Rule 2. Draw another ray from that same spot on the object, but this time, aim it straight through the dead center of the lens, the optical center. That ray goes straight through without bending at all. And boom. Where those two rays cross paths on the other side, that's exactly where your real, inverted image is formed. It's a perfect picture of the math we just did.
Whew, we've covered a ton of ground. To wrap things up, I want to leave you with a final cheat sheet. These are the 3 most common slip-ups I see students make. If you can just remember to avoid these 3 things, you're going to be in fantastic shape.
Let's lock these in. Number 1. The object distance, u, is pretty much always negative. Think back to our examples. The mirror problem, u was negative 30. The lens problem, u was negative 25. Forgetting that first minus sign is the number 1 trap. Number 2. The lens formula has a minus. Don't mix it up with the mirror's plus sign or the whole calculation goes wrong right from the start. And finally, number 3. The sign of your final answer v tells a story. Remember how v was negative in both our problems? For the mirror, it meant a real image. For the lens, it meant a virtual one. You have to know how to read that story correctly. You see, by focusing on that sign convention and really understanding the story behind the formulas, you're not just memorizing physics anymore, you're actually getting it. So the only question left is, are you ready to walk into that exam and absolutely master any numerical problem they can throw at you? Yeah, I think you are. Go get 'em.